Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome, and I apologise for the somewhat earlier start than usual, but thanks for coming. We've got sort of a busy day today, hence the early start. We actually have two talks this morning, both of which have a sort of computer vision flavour, so I thought before we started I would just take 60 seconds of your time and show you something from, which you may have seen, it's from the BBC from yesterday, like a very nice application of computer vision, and hopefully I'll be able to show you this. If the audio works, it should be self-explanatory, I hope.
The child just towards the top right of the picture is clearly beginning to struggle. With she turns to the bottom of the pool. Unless help arrives quickly, she has little chance of survival. Suddenly a red box appears on the screen. The computer has realised she's in trouble. The seconds tick by. Then the rescuer arrives and brings her to the surface. She's safe and thanks to a remarkable piece of equipment called Poseidon. This is the visible end of the side is a monitor at full size.
Very encouraging for people in the community. So, as I said, we have two talks. A question already, Simon. We haven't even introduced the speaker yet.
Who made the site?
I know very little about
Two
it.
of the people who we know who are on the scientific board are Olivia Twidger and Gerard Benjamin, so very well known computer vision and they're using the scientific. They've got a field medalist on the board as well. I don't know what he's doing.
Okay, there we go. Okay, so as I said, we have two talks this morning, both with a computer vision flavour. At 10:30, Canon Aachen is talking about segment-based inference in vision and speech. But first of all, Anita Cannon, also from the University of Toronto, and Anita supervised by Brendan Frey. And if you notice, there's a similarity in the names of the two speakers. This is not entirely coincidental. And Anita's going to talk about layers of appearance and motion.
So, I'm going to talk about a generative model for layers of appearance and motion. And this is a joint work with my advisor, Brendan Frey at University of Toronto and Nabosha OH at Microsoft Research. The goal here is very simple. So you have an image and you want to be able to decompose that image into its constituent variability, such as the image could have variability due to appearance, it could have variability due to lighting changes, and so on from frame to frame. So the goal is you want to be able to take an image and then decompose into these set of variabilities. But the problem is when you increase the number of variabilities that you're interested in, then there is a combinatorial way of explaining these variability. And therefore, it's often very difficult to decompose into all these variabilities. So typically, you take into account only a small number of these models that the rest of the things could be modeled differently, such as in the noise processor. So today, I'm going to focus just on modeling changes in appearance, deformations. Deformations are local changes, such as when your hand moves, there is a little bit of change locally that's happening. and the global transformations where you're shifted from frame to frame. And I'll explain what these are in a moment. So, for instance, here's a simple case where the observation is just the person walking across the street, across this static background, and the global transformation represents the change in the position of the person from here to all the way to the other end of the frame. And then the appearance change is the way the person changes. For instance, he has a leg movements and the hand movements and so on. So in this case, you are modeling the appearance with a separate model for the appearance. In this case, which is a factor analysis model, which actually does a linear dimensionality reduction. And then the position is modeled different using transformation variable. So there is so you're explicitly modeling two things. You're modeling the appearance and you're modeling the transformation. And everything else, maybe there's other changes that are happening, for instance, lighting, which would be accounted for in the noise model. So if you want to learn a good representation for the appearance, you need to first align the object. So you take each of the frames in the sequence and you have to do some sort of alignment. Only then, once you have the aligned images, then you can learn appearance of the object. But to do the alignment, you actually need to know the appearance of the object, because without good appearance of the object, you just can't do a good alignment. So there is a need for iteratively doing both. You have to somehow start doing both of these things jointly by learning appearance and then using that learned appearance to do the to estimate the transformation, and then given the transformation, you again do the learning the appearance. So there's an iterative procedure there. Then the other case is when you want to do dense motion estimation. What I mean by dense motion estimation is that you want to be able to track each pixel from one frame to another. For instance, this pixel here is tracked to a pixel in this frame, or you may want to do from here all the way up to here, and then and then all to here. And then here is another example where you're tracking this pixel from here to a pixel over here. Typical approaches here would take one of the frames as a reference frame and then use, for instance, they may use this as a reference frame and be able to track, and then using this as a reference, be able to position where this pixel goes. But then you can't use this as a reference in this case, because in each frame there are distinct regions that are unique to that frame. For instance, here you see more of these regions. So none of these frames can actually act as a reference. So in this case, again, you need to learn appearance as a representative appearance, and also use that appearance to do the transformation, or do the motion estimation. So the method we are approaching here is to use a common representation for object appearance, and use that representation to find the transformation that you need to actually be able to track the person. So, and the way we're going to do this is using the generative models. And what the generative model does is that it tells you how the image is formed. So it sort of gives you a structure of all the variability that you're interested in, how they interact, all these variables interact to explain your observation. And then now all the unknown variables that are there in the generative model can be obtained by performing inference, a procedure called inference, which is basically finding distributions over all the unknown variables in the model. And then you can learn the parameters that governs that model using the data by doing maximum likelihood estimation. So I'm going to actually start with a simple example, illustrative example, where in this case this is pretty illustrative because I'm only assuming there are only two objects in the scene, and how you can explain that, use it to learn appearances of objects and learn deformations. So the idea is that you just have two layers. You have a foreground layer and a background layer, so corresponding to two objects in the scene. So here's an appearance of the background object, which is just a static garden scene, and here is an appearance of the foreground object, which is a person. And then associated with this is a variable which we call the mask, which tells you the probability that that particular pixel actually belongs to the foreground. So if it's a black here, the corresponding pixel here in the foreground is not really a foreground pixel, but it's a background pixel. And if it's white, then it's probably the foreground pixel and not the background pixel. So also we have what we call the deformation vectors, which are just the motion vectors that tells you how these pixels should be actually deformed. And so for the foreground, you have an associated motion vector which we call u, and then for background, we have an associated motion vector which we call v. So the generative process is, so you basically take this motion vector, generate a motion. Okay, I'm going to actually show you a bigger picture later on, because it just doesn't fit in here. So here is a motion vector for the foreground. So every pixel tells you how that pixel should be actually deformed. And similarly for v, and then you take your background appearance, deform it according to this motion field, which is this, and then take your motion vector u, this motion field, and then deform the foreground appearance according to that, and then similarly the mask. And then you may want to apply global transformation that tells you how the pixel should be moved. So these are the global transformation vectors. And then you shift these deformed appearances and the mask according to the motion vector. So that's your deformation, deformed images and globally transformed images, and then combining them according to the mask. So when there's a white, you pick the corresponding foreground pixel, and if it's a black, you pick the background pixel, and then that's your observation. So you can see that from here, you actually at the very end, the person has been like scaled down, and then when he goes further and he's walking towards the camera, he becomes much larger, and this is taken care of by the deformation field. So here's
So you're distinguishing between this global motion and local deformations, and I'm wondering why. If you just did that little black matrixy thing with your deformation matrix, you've included the movement of the person. You can now combine these two into one.
Okay, so there are two parts I want to answer here. So this is just a representation of telling me where in the image this particular global transformation to occur. But I could possibly incorporate this into this deformation field, except that, as you'll see in my algorithm, I'm doing patch-based matching. So when you actually have to do global transformation, then you have to go from one end to the other end. Then you're going to sort of get more matches to match. And because at the other end, you may be actually able to find this. So this, by explicitly modeling the global transformation, you're sort of taking care of some of this, some of the problems you would have by doing this extensive matching. So you want to do matching locally so that you're not actually getting to bad local solutions at the other end. So, and then it also speeds up your computation because you're only searching local regions and you're not looking at all possible positions in the image. But I'll explain to it when I actually start explaining how to do the model in a lower scale. Yeah.
Because at the end of the day, you're only going to inform the foreground.
Right. Uh-huh. Oh, it does, because a priori you're independently sampling from this distribution mu to get your deformation field. But your foreground and your mask both gets deformed according to the deformation field, because there is a link between, because your mask is sort of tied to your foreground. So here's an example of a deformation field. This is your appearance, and here is your deformed. Here's an input image, and you want the foreground appearance to be deformed, and this is the deformation field. So it's like in the head region, it tells you that your head should be blown up a bit to explain your bigger head region in the foreground appearance in your input observation. And here's another example where your shirt collar should also be expanded to explain your observed foreground image. So I just want to go back here and then forget about the global transformation and explain a generative model for just how you would generate up to here, these images, and then compose to get your observation. So that should make it clear why you would actually want, whether you want to use the global transformation or not. Sometimes you may not need to use it. So the idea is that you take your image and then you decompose it into a set of overlapping patches. And then you draw each of these patches from a generative model, which I'll describe now. So a priori, you have your background and your foreground appearance and the mask. And then you have a deformation field, a vector for your background, which you represent by V, and then deformation for U. So if you don't have any deformation, you just take the corresponding patches from the background, foreground, and mask, and you would compose according to your mask. But if you did, so for instance, for deformation for background, you say that there is no motion. So that's that is static. And for the foreground, there is a motion vector that tells you to go right and down. So you actually take your patch and shift it down and right, and then go to this patch, and then similarly the mask. And then so you have deformed patch from the background, deformed patch from the foreground, and then the mask, and then you compose according to this distribution, which tells you that for each pixel in this intensity of each pixel in this patch is just a combination of foreground and background. Where if this pixel is black, so you have 1 minus mi is actually 1, so you will take the corresponding pixel from the background. And if this pixel is 1, then you would actually take it from the foreground. And that's your generative model. And then you also, in reality, you will also observe some noise, which you're going to assume it's a Gaussian noise with zero mean and variance sigma squared. So you would, for each pixel is independent, given your mask, your foreground appearance, and the background appearance. Just please stop me if you have more questions.
I'll ask a sort of mundane
Sure.
question. In the appearance, foreground appearance, the arm which is on our right hand side, his left arm, doesn't appear. Yet in video, because he's swinging his arms, there are some frames in which there's a lot of arm. And I'm wondering where the flesh-colored pixels come from to construct that.
Right. Okay. So I have two answers to this. The first answer is that it's actually, since you have this local search, it's actually looking for a reasonably close pixel intensities that are similar, and it's taking from it, which is actually a mistake, right? But the real thing I should actually be doing, is that when hands move, it actually goes front and forward. So I should actually have a 3-layered model. So where the third layer will actually be modeling my hands, or I should have a different representation, which I'm going to go back later, come to later, which actually tells me how to avoid that problem. But here it is a problem, and I'm glad that you actually noticed it, because you just can't, in that sequence, you can't do it with 2 layers. Even if it's doing it, if you actually look at the motion vectors, it's actually making a mistake there.
But the question is, why doesn't it add his arm to the foreground layer so that some images it can draw?
Oh, because it actually has it has it on the other side, right here. It has it on the side. So I'm thinking that the motion vectors is sufficient to actually go and get it from there.
But that would be a huge cost.
Yes, but then the problem is then it can't explain the shirt, right? The shirt here, it can explain that. Because unless it actually puts another spot over here, which says this is part of the hand. And I think that's also an issue with the local optimal solution too. It could have been that could be the case too. But I think the right way is where the hands is the third layer it's learning. Because sometimes the hand goes behind, and sometimes the hand goes front. Right?
Okay, so I guess the question is, part of the foreground can just disappear, right?
Yes, in the inferred mask, yeah. Right.
So that seems like another
Okay, I guess, so when you're looking at it locally, though, right, that may not be the case, because when it's looking at it locally, you have to have, when you do it like this, this portion is foreground, this portion is foreground, and this one, if it says it's a background, then it has to explain that in the background somehow.
Maybe we should move on.
Okay, sure. So that's another one. So once we have the model, you can write down, the simplest thing is to actually write down the bound and the log probability of the data. And I'm going to use, I'm going to use inference, an approximation to the true posterior distribution over all the variables, because it's intractable to do, and I can come back to why it's intractable if you want. So the idea is, So here's your set of all the frames or the entire video sequence. And you're writing down the log probability of these observations, which is set of frames. Then it's actually lower bounded by this quantity, which is summation over all the frames that you have, and the Z denotes all the patches in each frame, and then M is just the mask vector for that particular frame, and UV are the foreground and the background motion vectors for each patch. And this is my posterior distribution, which is for each patch you have a separate posterior for the motion vectors U and V, but the posterior for the mask is shared across the entire frame, and the joint distribution divided by the posterior. So this quantity here is just an approximation to the true posterior distribution that you'll have, which is Q of U, V, and M given everything, and over all the frames and patches. So in this case, we're assuming that the distribution of the mask, the prior distribution is a Bernoulli, and the posterior is also a Bernoulli distribution.
Question. You agree with the deformations, were they?
Yes.
So you don't have. Do you have a spatial prior on the deformation that encourages sort of smoothness or not?
Here I'm just assuming it's uniform spatial prior, but you could just make it as a Gaussian prior, or that will enforce that is more peaked along one region, right?
I just want to be sure I understand what you're trying to do. So you've explained how, if you knew the deformation field in the foreground and the background, then you could generate the picture.
Right.
But of course, what you're giving me is the picture.
Right.
So your task is to figure out what all of these immense number of variables is.
Right. Yes.
Just from the pictures.
Right. Yes.
Right. And you're going to tell us how you do that.
Right.
Okay. Good.
So the way you would do is, there are two things you have to do here, right? The first thing is you want to figure out for each frame what is this distribution over what are the values for all the variables that are there in that sequence. So that's this. So I should go here. So for each frame, you have to figure out what is the global we're not even looking at global transformation. What is this deformation vector? What is this inferred patch? And so on. So you do it for each frame. And you also need to have this global appearances, which is the background appearance and the foreground appearance. So there are two things. You have to have the parameters that are shared across all the frames, and you also have to infer for each frame what are its corresponding explanations. Oh, we are going to fix that. In this case, we're just fixing it as there's only one foreground object.
Oh, so you don't guess that. You say there are two.
Right, yes. But there are ways to do, ways we could do it, but we're not going to do that. So this is like one of the simplest things we could do when we begin. So this distribution here will tell you, these Q's will tell you for each frame what should be the explanations. And F and B and the P of M are things you need to learn. Right? These are shared across all the frames. So the way you would estimate all of this is to write down a cost function. And then in this case, we're actually doing a negative cost function, which is you want to maximize this quantity or minimize the negative of this. So here's how you do it. So first, to initialize, you take frames from the so you want to initialize the parameters, the foreground and the background. So you initialize it to take one of the frames, and then initialize that to foreground, take another, initialize to the background. And then you assume that the mask has a uniform distribution. So each pixel could have come from any of these foreground or background with almost equal probability. So we sort of slightly perturb that so that it doesn't stack into that local optimal solution. Now, and then we do this iterative estimation of inferring these explanations and learning the parameters. And then the typical method is called the expectation maximization algorithm, which does the maximum likelihood estimation. So it has two steps, the iterative steps. In the first step, it updates all the explanations, the distributions over the explanations for all your the deformation vectors for each patch and all the frames. And then it estimates the distribution over the mask for each frame. And in the M step, it updates the model parameters, the foreground, the background, and yeah. No, we're not doing that. Right. So our ultimate goal, like in the long-term goal, is you just give it the data. I mean, here we have sort of made a lot of assumptions, but then you really want to do is you just give it the data and you want things to come out of it, right? Totally unsupervised. You don't want to be sitting there and tuning parameters or doing any pre-processing step like background subtraction and then bring it in here. We don't want to do any of those. But I'll show you how background subtraction, for example, performs in this case and how our method does better. So it takes about, it's pretty reasonable. I think it's very slow, actually. You can't go real time or anything like that. For 40 frames with 160 by 120 video frame, it takes about 15 minutes per iterations, and you run it for about 10 to 15 minutes. So it's a pretty expensive process. So there's one thing I want to talk about. So we sort of made this thing that assuming that each patches are independent, which is not really the case because these are overlapping patches, and there are things that are shared across each patch, and we didn't even take into account that these frames comes from a video sequence, so there is some continuity there. But I'll show you one simple, even with the simple model, there is this n-force of constraints through the posterior distribution. So you don't have to worry about this expression here. So this is just Q of what is the probability that the ith pixel in the mask is 1. And then the denominator is just a normalizing constant that makes this to be a distribution. So Q of mi equal to 1 plus Q of mi equal to 0 should be 1, right? So this is the denominator. But let's look at the numerator. So what it does is that it takes so for update for a particular pixel I, it takes all the patches which shares the coordinate I, right? And then it minimizes the squared error between the intensity of that patch and then the foreground shifted by amount u, and then you sum over all possible values that you can take. So this is where the constraint is. So it sort of takes into account the influence of all the patches that attribute to that particular pixel, and then estimates your posterior. So that's one place where there is agreement, and you would see this kind of agreements in other update equations as well, like foreground updating the foreground appearance and so on. So I just thought that would be a nice point. Even if you assume that all patches are independent, you're sort of having this agreement happening. So I looked at a very simple model where I was just assuming that the appearances are all like parameters to the model. There is no distribution. You're not allowing for noise. But I just want to compare it with another model where you're actually taking into account this variability in the noise model for these appearances. So here's the work that I'm presenting now is actually an extension of flexible sprites work by Nebosha and Brennan in 2001. So the model there is you have an appearance for the background, you have appearance for the foreground, but then the foreground appearance is not a parameter, it's actually a distribution. So it's basically each pixel has its own variance. Okay. And then again, the mask is also not, the mask also has its own distribution with the mean and the variance. Now in this case, they're not modeling any deformations, they're only modeling the global transformations so there is only so you basically generate from the appearance class here, and then you operate from the appearance for the foreground, and then the masked appearance and then the masked generate from the distribution for the mask, and then you actually apply a global transformation, and that's your observation, and then you compose it using the usual way of composing. When the pixel is black, you take it from the background, and the mask pixel is white, you take it from the foreground, and then you compose. That's your observation. So in this case, again, there is leg motion of the leg that's modeled in the noise model, in the noise variance. So the appearance is much richer. The appearance representation is much richer because there is variance per pixel. But then you're modeling only very simple transformation, which is the shifts. But the current model is basically more deformable because you're allowed to each pixel to deform. But then since we are allowing this extra freedom, we're sort of saying that my foreground appearances and the background appearance should be fixed. It should not have its own variance. So that's like a comparison. So what does the deformation variable really do? Okay. So for the data that we've been looking at, if you do this flexible sprites, what happens is it learns a lot of variance around this region here in the leg, in the hands. And similarly, the mask also has a lot of variance. But then the foreground appearance or the mask appearance don't look really good because there is clear deformation going on in the sequence because the person is growing in size because he's moving towards the camera. And here's for the deformable sprites, you actually have a better foreground mean and then the mask. So one thing people do is first they do a background subtraction. So what they do is they take all the frames. If you compute the median, if the person has moved considerably far enough that you actually get the median will actually give you a good appearance for the background. And then you find out for each of the frame how different the intensity of each pixel is to the background estimate. And then you take the square and put a threshold. And then say these are foreground pixels. So we actually tried different thresholds to get the optimal thresholds that will actually pull out the person. And you can see that the background subtraction is still missing out on this on the main body region because this black shirt is very similar to the intensity of the greenery here. So I think like doing one of these pre-processing steps and letting your model learn from this pre-processing set may not be a very good idea. At least I'm not really keen on that. But so here's another one. This is like one of the toy examples I tried when I first started out this project. So there's only 6 frames where I'm moving towards the camera, and if you just take the flexible sprites, the one without the deformation field, and then learn the parameters, it's going to say most of these region which is not really changed to be part of the background because those are almost static. And so you sort of get very poor representation for the foreground. Now if you are modeling with the deformable sprites, okay, and then it sort of learns a very good appearance for the foreground, and then it fills in for all the so this region is always occluded, so you can't really find out what's behind these regions. But then for all the regions that are found in at least, all the pixels that are visible in at least one of the frames, it can actually fill in for those. But I'll actually show you a way of how you can actually, at least for when there is continuous texture, how you can fill in for these background. So it's not okay, I just want to try a little bit of frame interpolation. So in this, here is just single frame interpolation. Basically, between these 2 frames, what would be like halfway midpoint between these 2 frames? Okay, that's this frame here. You can see that it's capturing a lot of these motion in near the mouth region. And this is 10 frame interpolation, which is like between every adjacent frames, you actually insert 10 frames. So it's sort of blurry in the end. So it's not great, but there's still scope for improvement. So here's another example which actually leads into my other topic where, so here's a video sequence of person sort of dancing. And so here you can see that the background is changing a lot. So you have to actually learn a panoramic background to represent all the features that belong to the background. So here is a panoramic background. And then if you look at the foreground, in this case, it actually put in these 2 heads because both are equally prominent. So there's actually 2 heads here. And his body is kind of shrunk because a lot of these features are very similar, the black region. And here's the Inference. And then you can see that the lighting variations that are happening here because then it's like near this region, most of his portions of his face actually looks very similar to the background. It sort of misses out on those. But important thing is that we are sort of wasting a lot of space here because you don't need such a big appearance image at all for the foreground. It could have a very compact representation. And people have looked at, typically you don't have enough data to learn a good appearance model. People have looked at texture models where they were learn a model for the texture that are present in the data. But then if you but in a realistic scene, often the texture is pretty much heterogeneous. So just learning a simple texture model may not be sufficient. So one option we're thinking of is to use epidemic representation, where what the epidemic representation all is about is just learning a very compact representation of the image. So it actually throws away redundant texture that are present and learn some sort of compact representation. So here's an image, here's an epitome of the image. So you can see it has like the flowers and a little bit of the ground, and then most of the dog features because the dog texture keeps changing. So the way you would learn it is you take your image and then break it into a set of image patches of many sizes possibly, and then use those to learn. Start with the random mean epitome, and then find out where these patches actually fit into those into that image, and then update your epitome. So basically that's an idea. So once you learn the appearance epitome, you can take each patch and then figure out where it gets mapped to. So in this case, for instance, this patch here is mapped to many patches in the input image. Here's another one where this patch is actually mapped to many patches in the input image, so on. So we could extend this idea and then do image segmentation or finding layers in the single image. So if you're, instead of a video sequence, if you're just given a single image and you want to be able to decompose it into the foreground and the background, you could do this with this epidemic representation, because you have these patch constraints, and the patches provided by the appearance epitome and the mask epitome. But the more interesting thing is be able to fill in for the background. This is because you have this texture continuity. So you basically have, when you want to explain a patch in this region, for instance, you have to take two patches from the appearance epitome. So one patch will come from the foreground region, and another patch should come from the background region. Because of the texture continuity, you can actually start to fill in these background regions which you never saw at all. So here's a little video that it's a little too fast, but so you start with very random appearance epitome and the shape epitome, and then you start off say that there is a foreground and background explaining. So you take two patches from the appearance, and then you take a single patch from the shape, and then you compose, and then that you could put it in the foreground, the background, and the mask, and then you compose it as before. Like if this is a white, you would take it from the foreground. If it's a black, you take it from the background, and then explain your input image. And you can see that again, there's a little bit of hole that gets filled in later on in the iterations. Should do this, should practice this more. Like that region out here, if you actually see it one more time. Right there. That gets filled in later on because of influence of the shape epitome playing a role. It says that, okay, this region there can be a little bit of hole, so to fill that in. So here's an example of that I was mentioning, where the frames were all the frames had some feature that are unique to itself. So in that case, you can learn an epitome for the appearance and use that as a representation to actually track pixels across frames. And here's your frame, and here's the inferred mask. So I think going back to Tom Inca's question on the hand, I think epidemic representation will do better, because now you can actually have each patch, you're constrained to take it from any region, and so you could actually have a patch in the epitome that will actually help you in solving that problem. So there are challenges in, there is a real challenge of solving this visual scene analysis problem, but there is also sub-challenges that come along the way. One is at the representation level. What kind of, how do you model appearances? Do you want to model appearances as like, there are separate layers and each layer has its own appearance? Or do you want to do it as a palette where you're actually sharing these appearances in a single image and then using that? And then in the case of images, do you have to still work with intensities, or do you actually want to use other features to actually aid in your learning? So for instance, you want to use features from edges and so on that can actually help you learn better appearance models. Or And then there is this new topic of actually using bag of pixels, or do you want to have these vectorization of the pixels and so on. And then in the case of generative models, I think the important thing is in representing interactions. So you could take, if you have multi-layered scene, you could write down this scene as composition of these layers like this. Just keep going on. And then in that case, it's very difficult to actually come up with an efficient inverse algorithm that will actually learn appearances of all the layers in tandem. So if you write it in a more clever form, it sort of lets you in to do these do the inference much easily. So representing interactions is very crucial, I think. And then the choice of inference methods, especially when you're using, most of the time you're actually using approximate methods. And what would be a very good inference method to use for a problem at hand. And even if you're using, say, approximation like variational methods, how much interactions should you actually preserve and still have computational feasible, and what kind of interactions should you actually take into account? So in that case, before it was important for me to actually have a posterior where the deformation field for the foreground and the background are tied. If I actually had this as Q of U times Q of V, then it's much more harder to solve the problem. That interaction between U and V was giant interaction between U and V was very important for the problem, because I started with Q of U times Q of V and it was really bad. So I think that's pretty much it. So, yeah.
Thank you very much.
Okay, thanks. Thank you.
Lots of questions. I'd like to start. So, in your original model, if I understood it correctly, the prior of the deformations had independent pixels, independent across space and independent across time. But we have this very strong piece of prior knowledge about real videos. There's a tremendously strong correlation between the displacement of neighbouring pixels and neighbouring in space and neighbouring in time. And it would seem that adding that sort of prior information should be a huge win. When you go to the epitome, do you not sort of lose that? Because now you're saying that the left arm and the right arm are going to be both sort of pulled from the same place. In other words, you've thrown away except maybe at a very small patch level, you've sort of thrown away the opportunity to include smoothness.
So one way you could do is do what's called the video epitomies, where you're sort of saying, I'm going to preserve the time smooth constraint by using, instead of a single image, I'm going to use a video image, right? So basically video epitome. So you basically have a few frames on the video, and then now you're sort of saying so you're going to have this constraint formed along those lines. So you don't have to have a single image to do it. And I think in that case you'll actually have, if you actually have your, I'm not saying exactly video epitome, the video epitome as in CVPR is sort of different, but the one I'm referring to is different. But so if you actually have your hand like this and here like that, right? So your sequence of epitomes would actually correspond to these regions. So you can say that if you have a portion of the video, in the first frame of the video epitome, you would have your hand like this. The second frame will be like this, and the third frame will be like this. So you can sort of model that across time as well. I think that's another way to do this. But if you're sort of starting with a single image and if you want to tie it across using the deformation field, I think that is possible too, because you could enforce constraints into the instead of saying that each patch is independent, you can say that if this patch moves here, then the next patch should actually be in a region very close to it in the epitome. That constraint can also be enforced. So there are two options, two ways to do this. One is either in the epitome itself, where you have multiple epitomes which shares, or the other one is to actually do it in the deformation vector, where you say that if this mapped superposition here, and then the next patch or the same patch in the next frame should actually be located in the epitome in the closest position. That could be enforced as well. Yeah.
I know it's boring, but I can't help worrying about the computational complexity. I mean, you gave us a statistic in the middle, which I did a little calculation here that suggests that what you're doing is about 1,000 times too slow, and you still need more complexity. And I heard recently that Moore's law stopped. So, is there something, you know, that captures the elegant compositionality of your approach without getting bogged down in these highly combinatorial computations? Have you got any sort of view of that?
So one view is that in the past few years, the speed has, like my old code, if I look at it and then I run it now, it runs much faster. So I'm hoping that in the long run, you would actually have really faster computers. But that's, apart from that, I think we're actually looking into ways of doing fast inference and learning. So, which will actually be able to speed up a lot of our computations. For instance, when we started with epitomic work, it was really slow the first time when we did it, because we're looking at each batch and then doing it individually. But then if you actually use a modified version of the cumulative sum trick, it runs much faster. So I'm thinking that it's better to always start with a good model, even though the computation is really is really a big killer. But you actually start with a very good model, and then you can actually sit and kind of find ways to do faster inference and so on. But right now, top of mind, I don't know how to make this into 1 second or even 1 minute per iteration. I don't know how to do it right now. But
would you consider giving up the full representation of probability distributions, for example, over displacement? So at every point, you've got this UV table to carry around.
Right.
I mean, is there some room for compromise there?
So I think the one compromise I sort of do, it's not quite a compromise, is that if you actually look at the entire table, most of the values will be close to 0, because you're not going to, because you're looking at a large number of these UV values that you're looking at. So one thing we do is, instead of keeping around this entire table, you keep around like top 50 or 100 of these. So you say that I'm only, most of the other values are close to 0, so I don't really have to care. So I just keep the top 100 and then have a distribution over these top 100 values for each batch. So I think that's kind of a thing we do. And I don't know how whether the smoothness constraint will actually reduce this number from 100 to say 50 or 10. I haven't really looked into that, but that's another thing.
Clarification, just to correct my esteemed colleague, Moore's law hasn't stopped. In a sense, we still have more transistors than ever, year by year, on a piece of silicon. What has stopped is our ability to work out what to do with them. The claimed solution is we're going to go multi-core and have parallel computing. So one question is, how might parallel computing help these algorithms? But there's a gotcha there. What is the communication and memory architecture? That may well impact the scalability of some of your solutions. And that could be actually an interesting issue in the vision space.
Sorry?
Your global transform is just translation.
Right.
So why not include scale?
Oh, we could do it. Jonathan has it on the on the layer. We could do it on the. We could include any kind of transformations you're interested in to the global. Yeah. So if you actually talk to John Wynn right there, he actually has it for the flexible sprites work, where there is only where you're not actually doing any deformation, but just do global transformations.
You've talked about extending this model to additional layers. Do you see any issues with performing variations? Not so much the computational expense, but just converting as you increase these complexities?
Oh, on this particular, on the deformation model, or? My experience with the flexible sprites model, right, where you're actually not looking at patches, but you're looking at the images, it wasn't a big problem. But the only thing is that you have to be careful in how you're doing these updates. That's what I found. And I think with extension this to the multiple layers would still be the same thing. It's just that you have to be a little more careful about how do you initialize things. Not careful in the sense, there are multiple schemes by which you can start initialization. Like even if you're doing random initialization, do you actually start with if there are L layers that you're interested in, do you actually update all the L layers at the same time, or do you do, for first few iterations, do one layer and then add in another layer and so on? So those are the things that are interesting. I think if you do that a little carefully, it should be all right. That's my.
So you think that as you increase the complexity of the generative model and have added additional modeling for the innovation and so forth, you're not going to at some point encounter too large a latent space to allow to avoid those. You just assume that there's an initialization.
No, I think when you actually increase the hierarchical generative models, there is still a problem with the local optimal solution. Actually, Canon is going to talk next about that. But sorry for the advertisement. But but I think when we get there, I think there must be a way to solve it. I think that every problem has a solution. You just have to dig in close. But that's all I could say. So if I understand your question, you're saying that, okay, if you have a 100 by 100 image, then you have 100 square patches, then you basically want to throw away some of these patches. Maybe look at every other overlapping patch or every fifth overlapping patch and do it. I actually look at all possible overlapping patches. Then for 100 by 100, so I look at 100 square patches. But the only advantage I have is that I can actually compute for a particular UV vector. I can compute the distribution for that UV vector. I can compute the distribution for all the patches in tandem. But if you actually remove that constraint and say that you're only looking at a fixed set of these patches, but you want to have enough overlapping patches. You don't want to, like, say, if this is 10 by 10 patch, you don't want to go first location, then go to the 11th location and take the next patch. You don't want to do that because you need to have that coherency. In that case, you're decreasing the number of patches, but I don't know of a elegant solution where you can actually get these vectors simultaneously. So there's two issues. If you do it one patch at a time, that's more expensive than if you actually do all the patches at the same time. But the only thing is now you're looking at more patches than may be needed, because if you don't have to really look at all overlapping patches, I think you can actually skip some of them, but then you have to figure out a computationally speed up way to figure out these distributions fast. So I think that's the problem there.
So we'll meet again at 10:30 for Canon's talk. And I noticed that Anita's laptop says 5:12